presenter today is Dirk Petring. So Dirk is group leader for macro joining and cutting at Fraunhofer Institute of the Laser Technology. He's an internationally recognized as a leading figure in these processes, and he's very active on the international scene. Certainly when I joined the laser scene, Dirk was very present internationally and very welcoming. So, you know, he's been supporting ALU's workshops and conferences for the past 2 decades. And today it's my pleasure to introduce Dirk, who's going to speak on milestones of laser beam cutting and the look ahead. Over to you, Dirk.
Okay, good morning, everybody. I hope you see my slides and hear my voice. Unfortunately, I lost the connection to the technical support, but let's start nevertheless. I believe they will manage something as well. Thank you. There were some thumbs up for me. Thank you. Yeah, first of all, thank you for the kind introduction, John. It's always a pleasure to speak at an ALU conference. And I have to say congratulations to the organization by especially Dave, of course, and the whole ALU team. I have the feeling you made it, and we can even enjoy a virtual conference. Of course, I would have preferred to come to Daventry last year and celebrate the 25th anniversary. But so today we have to say congratulations on the 25th +1 anniversary, and let's celebrate that. So laser beam cutting, one of my favorite subjects since about 35 years, but the cutting process is existing since more than 50 years. And we will speak a little bit about the history and of course also what comes next. Contents is like the title. I will separate the milestones in technical development, industrial implementation, and scientific understanding a little bit. Of course, I can only give examples, and I will have to skip many important pioneer work within the 25 minutes I have, of course. And second, of course, a look ahead, perhaps for some of you even more interesting than looking only back. But this will be a shorter part of this presentation. I will also not explain the laser cutting process, if then only with these 2 pictures. It's simply using a light source, focusing it with a lens, and then putting the focus on or into the workpiece and cut. That's all. I think many of us as child tried this already. Of course, there is always a development, distance control, better beam shaping, and a little bit better handling of the tools, things like that. But in fact, it's all not that serious or secret or difficult. The details are the difficult things, of course. Coming back to the milestones and the technical development, industrial implementation, scientific understanding. In fact, this is also part of the ALU mission. And I can only recommend become a member of ALU, and then you will always be informed about the latest developments. You will get experience in the industrial implementations and also expertise in the scientific understanding. So I think there are many good reasons to join this, I would say, best laser club in the world, at least in Europe. Otherwise, you miss something if you want to work and use lasers. And the second point regarding the trends, of course, we have some not so nice trends recently. I would say in the laser community, we should make it different than the politics. We should join perhaps under something one could call ALUnion, because all starts in Great Britain or United Kingdom, as we will say later. Here we see it. Peter Holcroft from TWI and Arthur Sullivan invented something in 1967. And I was very sorry when I read in the ALU magazine of last year in autumn that Peter passed away in August. And I was very impressed of what Paul Hilton was writing in that magazine about the life, work, and achievements of Peter. Really impressive. And let's think about him and of him for a very short time, at least. His work was fundamental because he was the first to install a system which can cut metal sheets by using oxygen as the assistant gas and using the exothermal reaction of this process as an additional heat source. We do not go through the parameters here. What is quite funny is that at that time, of course, there were no zinc selenide optics. This was all made from the potassium chloride, the lens as well as the protective window of the nozzle to build up the pressure. Funny story behind it, the feed thickness was up to 2.5 millimeter, which is 1/10 of an inch. And what made the Times out of it, UK newspaper, they were writing oxygen laser cuts 1 to 10 inch stainless steel, simply moving this line into the horizontal. So always be careful with messages in newspapers, whether it is about laser or the royal family. These are my motivators, I call them. I could also say my private hall of fame of laser cutting. Of course, again, a lot of people are missing here, but for me personally, these were the people who motivated me when I started in '86 with laser material processing to look at the cutting process in more detail. Of course, Peter already mentioned very fundamental work. And a little bit more than 10 years later, Yoshiaki Arata invested the process in Japan, invested the process in Japan, and he found out one of the first cutting models, the so-called Arata effect, as we laser cutters call it, namely that during the laser cutting with oxygen, the burning front can leave the laser zone, then the burning process is diminished, the laser is catching up again and heating up again to ignition temperature, and the burning process is starting again. And this cycle was recognized by Arata and also visualized in some of the first high-speed videos of this process. Very impressive and still valid. The next guy, Flemming Olsen from Denmark, he's famous for the recognition about the polarization effects of laser cutting. This sounds quite physical and special, but at those times when the high power lasers were folded after the first lasers, which only having one linear resonator, people did not understand the change of the process with the cutting direction. And this linear polarization produced by the folded resonators was in fact the process, because if you change the cutting direction and the linear polarization keeps in a constant direction, the process changes, and this is explainable by the Fresnel absorption. And this was fundamentally explained and also demonstrated by Flemming. Regarding modeling work and simulation, I have to say Dieter Schuecker from Austria was an inspiration for me. When I started, he had already some models about laser cutting, which motivated me to also deal with this, not only making empirical investigations, but trying to understand and to describe and to calculate the process. Thank you, Dieter, for that. And of course, we may not miss Brooke Ward. He was the first to recognize the supersonic effects in laser beam cutting by making Schlieren diagnostics of the free jet and also of the jet above the workpiece, and also by making pressure measurements and many other things. He was really the initiator of gas jet understanding in laser cutting. And we followed this up later on with own work. And of course, one of my best friends, John Powell, I would say he is internationally recognized as Mr. Laser Cutting. Latest when he published the first edition of his famous laser cutting book in 1993. And yeah, he is in fact a genius because he has so many jobs, so many capabilities. He is a professor in Sweden. He has a job shop in Nottingham. He is also a professor in Nottingham itself. He's a musician. And most of all, he is a stand-up comedian. And so it's always a pleasure to meet him. Now we get a little bit more serious again, or more straightforward. Let's look first at the automotive implementations a little bit in 3 slides. During these early years, I would say, as far as I know, the first automotive application of laser cutting thin sheets was at Ford in Cologne. If somebody has an earlier address, please send it to me so I can change my results and my list of all these dates and companies. So at least in 1975, Ford started to do cutting of prototypes and small batches with a Messer-Griesheim system. You can see on the right picture. And already a flying optics, as you see. And others followed, of course. For example, BMW in Munich in 1980, already then with a little bit higher power, 600 watt. And again, at these times, Messer-Griesheim system. We make a big jump to the late 80s when Renault, you see it here on the left side, started with 3D cutting in the body shop. This was the first serial production in automotive industry. And the application was customizing. This was the early 3D application of laser cutting at the automotive OEMs, because the option holes for different variants of the cars could be made very flexible with a laser system. For example, in the Renault, it was the rear window wiper mounting holes. Some cars do not have a rear window wiper. The body side light holes for special lights, and the seatbelt mounting holes in the car. These are examples about customizing products with flexible laser technology. Meanwhile, laser is a standard tool also in automotive industry, mainly for welding, one has to say, but also for cutting. One example here from 2003 is an interesting application at BMW, where the hydroformed cross members of the aluminum front end are cut for the BMW 5 and 6 series, starting in 2003. This is a 2-head cantilever system, a very special design system from HELT. And it was equipped with 2 slab lasers, the CO2 lasers in the market in those times with the highest beam quality, and nearly diffraction limited and square 1. So it could realize a quite high efficiency in aluminium with quite high speeds and accuracy. Yeah, and right now, without laser, we would not have these high strength steels in the car. Or to say it with other words, they would be much more expensive, because this hot pressed steel components, as they are used for B pillars, A pillars, and other structural parts of the cars, have a very high strength and ductility and good crash behavior. So on the other hand, they cannot be cut very economical with conventional mechanical tools by punching. So the laser is the best choice, and this started in very high numbers, latest in 2012 at Volkswagen, with the first installation having already 10 3D systems, in that case from Trumpf, to cut the A, B pillar and side components of the Golf, different Golf versions, and the Tiguan SUV. So this was a short, quick walk through the automotive development of laser cutting. Of course, it's it's a little bit more behind all this. So we come back to the basics. And I would like to show you 2 pictures of our lab, which we started in 1906 in Aachen at Fraunhofer ILT with a Rufin-Sina 1.5 kilowatt system, CO2 laser, DC excited, of course, and a 5-axis cutting system with the XY table and the rotating and inclination head and Z-axis. So what we did at that time, we thought stainless steel is not, it's not appropriate to cut stainless steel with oxygen because we lose all the good properties regarding corrosion resistance of the steel. So we started cutting with nitrogen. And yeah, this is one of the first results published in '88, a 6 millimeter stainless steel plate cut by this system in laboratory. And yeah, what was new, in fact, was at that time quite high pressure. It was difficult to get lenses who could resist this high pressure. Today, this is a standard pressure, and high pressure is 20 bars. So quite big nozzle, bigger than the standard nozzles at least. And what was important, non-centric adjustment of the nozzle to get more gas into the curve. Small nozzle distance, long focal lengths, not the standard 5-inch lengths, which was in every system in those days. And last but not least, we had a ring mode. In that case, a standard beam mode of this special roofing system. So we were lucky for this to have this beam distribution already at those times to profit from the more stable process. What was really important for us regarding development was not only understanding the laser workpiece interaction, but also to understand the contribution of the gas jet, the properties, the specification of the gas jet, and this means the gas jet in the curve. How does it behave? So we simply continued the work of Brooke Ward, but in this case, not only looking above the sheet or in the free jet, but also into the curve through simulated curve channels. And by this, we could study the supersonic effects, shock waves, compression and expansion waves reflected in the curve, boundary layer separation, and things like that. And we could study the parameter dependencies of this flow behavior to optimize a nozzle design and other gas parameters. The funny, or for us quite strenuous thing was that there was a lot of skepticism in those days about laser beam fusion cutting. So these are some citations, some comments of the skeptics. Supersonic flow in the curve is impossible. We really got this message from flow experts at universities. They assumed you have a perpendicular shock above the sheet, but it is an inclined shock, what we saw in the picture also. Gas consumption is too high, laser power demand is much too high, only for thin steel. If for any steel, it's uneconomical and will always be a niche application, if any. These were the words from the experts outside of our laboratory. So nevertheless, we continued because we found partners, especially Thyssen in those days, doing projects with us in the 90s regarding thick sheet cutting with nitrogen and also high-speed cutting with nitrogen. And of course, we continued to deal with all these basics of the cutting gas and the physical interaction, and also looking at the metallography. Because the steel supplier, Thyssen, of course, was interested. What about the corrosion resistance? What about the hardness of these cuts compared to conventional cutting processes, plasma or mechanical cutting process? And the laser was the winner. And so after more refinement of all these things, we were lucky to support the first industrial installation of such kind of high power system. It was at that time a 6 kilowatt CO2 laser system cutting up to 18 millimeter, starting in 1903 at the Thyssen company. And later also structural steel was cut at the shipyard in Germany since the year 2000. So there were some first implementations, but the big success story of the six-section oxide-free cutting of stainless started a little bit later. Nevertheless, a short list again to see how things develop. 6 millimeter in 86, 15 in 89, and in 96 for the ITER project, then 40 millimeter, being at that time still a laboratory result. Let's switch quickly to the high-speed cutting. High-speed cutting was always a topic for us since the beginning, and one of the very special applications was the slitting of electrical steel. And what we found fundamentally was that increasing the intensity of the laser beam, and by this the possible speed, the process is changing from a simple cutting front to some kind of vapor capillary due to the melt driven, like in a welding capillary, around the laser and then blown out. You see here from the bottom, the high-speed video image, here the exit of the capillary, and here the melt behind that, ejected out of the curve. Yeah, we did a lot of work again together with Thyssen. We built up a slitting line with 8 lasers even. We also tested neodym-YAG lasers already in 96, reaching this, achieving the same speed, but with double the power. Quite perhaps astonishing or not so well known. Peter Leiminger was at that time a student in my group, and he was writing his student's thesis on this topic. Yeah, a big machine with 8 CO2 lasers was built up as a pilot line. And if you see this beam guiding system and compare it with the possibilities of fiber lasers today, you see the big difference from that time to what we have today. Process development continued, and we also moved, of course, to the fiber laser, calculating the possible limits and nearly reaching the physical limits. Of course, you never reach it completely because some parameter is always a little bit down, perhaps 5% or so. And of course, also the model and the simulation is not perfect. It's still an approximation, but works quite well to show us the target we have to achieve. Otherwise, we would have never achieved, because in empirical investigations, you find the high speed and say, oh, that's it, without knowing the real limit. And finally, we developed a process for Honda for their first laser blanking line in Japan, where they today cut 18,700 parts per day. Since 2013, or better to say 14, the installation was 2013, and this is a quite impressive machine with a 10G moving system. This means a very high dynamic process. Cutting during the running coil, of course. Short to the laser sources, very quickly, we had 2 laser sources in 2005, 2 fiber laser systems, cutting systems, I have to say, 1 Italian and 1 Indian. And some years later, we had already these numbers here, and it continued getting more and more. And in 2013, I stopped to make this market search because too many systems already and system suppliers were on the market. Today we have perhaps 100 or so. Especially in China, the number of system suppliers is very big, but also worldwide. So a lot of people want to share and profit from this process. It is still making 40% of the whole industrial laser revenues. So it's still quite attractive and still something to do. Of course, you know all about this battle regarding improvement of fiber laser cutting. By the way, already in 2003, with enough power and the right focusing conditions, the quality was not so bad, at least in 10 millimeter stainless steel. So meanwhile, however, there are so many intelligent solutions to form the beam. I call it here the Lords of the Rings, because most people believe the ring is the best. The ring is one example. The ring is the best for certain cutting applications, for sure, not always. And this is why today the beam shaping is variable, can be switched. Unfortunately, we have no time to go through these in detail. Very intelligent patterns, a big amount of patents, and still growing. regarding beam shaping, not only for cutting, of course, also for welding and other processes. Still new possibilities, and yeah, we also work in this field since many years, and have also partly even solutions with spherical optics in the right combination to avoid the adjustment sensitivity of aspherical optics. Yeah, the last latest technical innovations, to mention only 4 from 2017 to 2020. Of course, I call it touchdown nozzle of TRUMPF, allowing a closed contact of the nozzle during cutting, and this is of course significantly, I would say dramatically, improving the efficiency of the gas jet. You can reduce the gas pressure and nevertheless have an excellent cut quality. This kind of idea is quite old, but what you see is, meanwhile, the competition is hard, and meanwhile, these kind of ideas find excellent technical solutions and also utilization in the market. Another example is the active speed control of TRUMPF with a video camera observing the process through the curve, and this is working at thicknesses above 4 mm, of course not at high speeds in the thin section range, but very well in the case of cutting rusty sheets and predicting when to slow down the speed to avoid reduced quality. Another very famous example is, of course, the Ventis of Armada, first installation in Europe in 2019 with the wobble technology, which is offering, of course, still a lot of new insight and new methods, and perhaps its patented patterns to improve certain cutting process. And last but not least, 40 kilowatt. This is the shocker we got September last year from China, where Bodor introduced a 40 kilowatt laser system. So the power is still increasing, typically today between 10 and 20 kilowatt. I spoke already about the market. Some short words about what we plan right now, or where we're still working on. Beam shaping rules, not only beam shaping tests, but understanding the rules, why which beam shape is the best. We found out that acoustic resonances in the curve can improve the quality, and our plan is to amplify these resonances. Of course, we utilize machine learning and inference engines, or we plan to do. We are still learning in it, but we're starting quite big projects in that field right now to close the loop and find closed loop controls for and higher automation in laser cutting. Laser blanking is still, there are still developments with more lasers in one machine and multifunctional processing, combining the flexibility not only in one processes, but in more. I skipped the lessons learned. You can read it later on. And thank you for your attention. I hope I'm still online, because I do not see the technical support. But it's my fault. I switch now to the, here we are. Okay, now I see it again. Thank you.
Thank you, Dirk, for an excellent presentation. A really good look back at the history of laser cutting, and good to see some of the deep thoughts in your mind on what the trends might be going forward. Certainly valuable to a lot of research institutes, I'm sure. I was just wondering, perhaps if you could, we just have a couple of minutes now just for some final questions. I was just wondering if you could perhaps summarize what the current state of play is between fiber and CO2 lasers, and where that crossover is for anyone who's looking to buy a new laser cutting system.
That's a good question. And the bad thing, what I say no, is perhaps already an old story tomorrow, but so this is a very dynamic situation. What we see in lab, also in the cooperation with system suppliers and within our projects with them, that I would say in former times we said 4 mm is the limit, the break even or crossing point. Today it might be at 6 or 8 mm. What one has to say, the quality is dramatically improved, even in 10 and 15 millimeter. But if you, and it is better, I would say, than a standard CO2 laser cut. So standard CO2 laser cut.
Thank you, Dirk. Sorry to interrupt. I'm being told we have 20 seconds until the session ends.
Okay.
I do apologise. I'd like to thank again both Dirk and Furumoto San for the plenary presentations this morning. The next sessions will start in half an hour at 10:45, and we look forward to seeing you then. Thank you again to Dirk and Tatsuaki. Thank you.
Thank you very much.